This is part 2 in the classification in ArcPro series. Part 1 being unsupervised classification. Part 2 is supervised classification, and part 3 will be accuracy assessment of both of those outputs. So, of course, the main difference between unsupervised and supervised is training. So we will train the algorithm, we will supervise it based on a set of sample points or polygons. In our case, we're going to use polygons. So to begin our classification workflow, we're going to highlight this guy here, and we're first going to make our training samples. And we could do this within the classification wizard, but don't, because you can't save them, oddly. So we're going to go classification tools into the training samples manager. Now you're going to see, first of all, there's a schema that's already brought up here from the National Land Cover Dataset 2011 that one may want to use, but frequently they're going to want to bring in their own schema instead. And so that's what we're going to do. You're going to click on this. You'll be clicking on a different one, but this is my Central Valley 3-class schema, which establishes class names, number of classes, and colors that they will default to when the classification is done. So now we are ready to start adding training polygons, and the goal here is to efficiently capture the range of within class variability of your classes, so that if you're wanting to classify this whole image, you are training on all the different relevant land cover types in that image, so you don't have anything that's that the classifier is running into that it doesn't know what it is at the time of applying the classifier to the unknown pixels. So I like to use polygons for training just because it's efficient. It gets you a bundle of pixels all together, but still it is better practice to have more small polygons rather than big polygons, because then you're presumably covering more of the image. So what I'm going to do now is only grab like 4 or 5 from each class, but you'll be doing at least 10 from each class. Additionally, you can sort of base how many polygons you do on the assumed within class heterogeneity of the class. So water is very homogeneous, so you don't need very much training data. Whereas our bear class, is somewhat urban, some out here, is pretty heterogeneous, and so you need more polygons to capture that variability. So let's do this. I like this little tool, this freehand guy. I zoom in, grab a water, maybe grab one in here because it could be shallower and have some different characteristics, and one out here. Call that good. Move on, click bear, and bear, I've got some urban stuff. Now I probably wouldn't do it here because I might like some of these pixels to ultimately be classified as vegetation and some as bear. That might be asking too much, but maybe it'll work. So I'll pick ones that are obviously bear based on this 743 image, where high redness is going to indicate reflecting a lot of shortwave infrared too, which is definitely not happening in robust vegetation. So the robust vegetation is green because it's band 4. So let's see, bear, and let's go over here. So this was a tricky area of like what is bear and what is veg. In the previous video, I decided that this vaguely green stuff was veg. This red stuff is certainly bear, and that this whitish red stuff is also going to be considered bear. And that's pretty obvious. So some of the stuff is going to be a little tricky. I might just grab this kind of edge case. Okay, I think that's good for bear. And veg, I'm going to take some of these bright green areas. Again, not a ton of heterogeneity here because it's mostly just like vigorously growing ag land. But we'll grab this darker area here. Okay, so you'll do more of these, but I think that's okay for now. And I'm going to want to save these off because we're going to now check the spectral characteristics of the training data to see if we think that a classifier can even really work. So I'll go to my default project folder and I will save these as CV training polys.shp. So you'll be doing a similar thing, and the naming is important to name it exactly in a certain way so that you can ingest it into R easily. So something that ArcGIS is not good at is evaluating spectral characteristics in advance of running a classifier. ArcGIS is a little more point and shoot and hope you get it right, but we in a remote sensing class want to look a little bit deeper. So we take a brief sojourn into R where all we'll be doing is pressing buttons. So this RMD is going to be located in the same folder as your data, which is critical. And we're going to be running through these chunks to look at some of the training data. So again, we're going to ingest the raster and the training shapefile. Let's see, CV, is that capitalized? So again, the names need to be exactly the same. Hopefully that's true. So we're just doing some housekeeping stuff, ingesting the data. We have our spectra. We have 3,752 pixels. So nothing to see yet, but here we go. Here's the first thing we're going to see. We're going to print out the class pixel and polygon summary table. So we have this many pixels per class and that many unique polygons. So that gives you a first glance at like, do you have enough data to feed the classifier? Now we're going to look at our spectral variability. So our first fun chart here, where you're seeing mean and standard deviation spectra for the three classes. And this is your chance to assess whether you think these classes are going to be separable, or do they, basically look the same. And I think we could agree that in this case, these classes are extremely separable. They are very different in a number of different ways, near infrared, short-wave infrared, like minimal overlap. So these should probably be classified with high accuracy without too much effort, assuming I made the validation points the same way I made the training polygons. So your version in DC will not be so straightforward. So we'll also look at the histograms for each band as another way to look how do these classes, how much within class variability is there for a given band and how far apart are the bands from each other. And then I'll just skip down to this final, or a final metric that we haven't talked about in class because it's a little complicated under the hood, but this is called the Jeffreys-Matsushita distance, which is just a statistical distance between a multivariate like distribution. And so multivariate just means we have 6 bands, so there are multiple variables. And this is a way of seeing how separable the classes are. So the values are going to range from 0 to 2, and any values that are near 2 are going to be near perfect separability, which is good. So here's, well, let's look the normal way. You'd go down and see this is your output here. And so veg from bear, almost exactly 2. Water from bear, 2. These are extremely separable like we saw before. So I think we can proceed nicely without needing to go back and like get some new polygons or even, add some new or add some different classes, like do we need a dead grass and a live grass class, etc. All right, so back here, and let's do the classification. So now we can go into the classification wizard, And this is not where it starts. Okay, this is where it starts. We're doing supervised classification. It is pixel-based, not object-based. Our schema, let's see if we already have that, is our CV. You'll need to go in and grab the schema, maybe. And our output location is going to be in the project default folder. Let's move on. We've already got our training. Oh wait, sorry. This is now where we can add in our training samples here because we've made them and saved them. So back to our folders in the default folder. Sorry, in the default folder. Sorry for jumping around a little bit. Now, if you go into your default folder and you do not see the training polygons that you made, you may need to just close Arc and open up again. I've had to do that every single time, which is a little annoying, but it's not extra work beyond that quick restart. So here's my training polygons, and we're not going to do a reference data set. So all of the training samples that I already made are here, and so we can scoop through here. And now we're choosing the classifier, and we're going to do maximum likelihood because it lines up with what we did in class. And we'll run that. And it produces a preview. I'm not sure why it does this exactly. This is not like the final result. Maybe it's just so you can compare classifiers visually. I'm not sure, but we'll just keep going. So we're not done yet. We'll hit next again. And now we're going to make the real classification. And so we definitely want to rename this. I'll put ML Central Valley 3 class. And we can just ignore the rest of this and run. Okay, so you can see, I'm going to see if I can get rid of this. Okay, so we just have our output. And so, did it do a good job? I don't know. We'll have to quantitatively assess it. Looks like it didn't exactly do the veg that I intended over here. Just for fun, I'm also like, okay, we've done all this work. Why don't we test different classifiers? Like, you won't have to do this necessarily, but if we go back, we can also choose these more modern classifiers, random trees or support vector machine. So let's do random trees and run that. And you can see that you do get a different result. Unclear what's better. We'd need to do a accuracy assessment on both, and that will be in the next video.